Dear students, I welcome all of you to the first lesson on statistical mechanics. I hope statistical mechanics is a new topic for you, but you might heard about statistics and mechanics separately. Statistics is the branch of mathematics that deals with the collection, organization, analysis, interpretation, and presentation of large amount of data. And mechanics, as you know, is the branch of physics dealing with the study of motion. In statistical mechanics, the statistics is combined with mechanics. Statistical mechanics is based on statistical methods, probability theory, and the physical laws. What is the purpose of statistical mechanics? We can use statistical mechanics to study certain systems which contains large number of particles. For example, you consider the gas molecules in a room. We know that there are large number of gas molecules in a room, and the temperature inside the room depends on the kinetic energy of the gas molecules. So it is impossible to analyze the velocity and kinetic energy of each gas molecules. In such situations, we use statistical mechanics to draw important conclusions. Another example is free electrons in metals. We know that metals are good conductors, and many property of metals is because of the presence of free electrons. And there are large number of free electrons in the metals, and it is impossible to study the energy and velocity of each electron. In this situation also, we use statistical techniques along with basic physics laws to study the system. Statistical mechanics has many applications in many branches of physics. Statistical mechanics is one of the pillars of modern physics. So, to study statistical mechanics, you should first know some basics of probability. So here we first study the basic probability theory. Probability of an event may be defined as the ratio of the number of cases in which the event occurs to the total number of cases. So the probability of an event P may be defined as the number of cases in which the event occurs divided by total number of cases. And this formula will be applicable in some special cases only that we will study later. So this formula can be more understood by considering an example. Suppose we are throwing a coin. We know that if we toss a coin, there are only two outcomes possible. It will be either the head or tail. So the event can occur in a total number of two equally likely ways. Equally likely ways means the probability for the head to occur is same to the probability for the tail to occur. So the probability of the head may come up is half, because from this equation we know that total number of cases is 2, and the probability for the head to occur is 1. Sorry, the number of cases in which the head occurs will be 1. So the probability will be 1 by 2. Similarly, the probability of tail may come up is also half. Another example we can consider is throwing a dice. We know that in a dice there is 6 faces. So all outcomes are equally likely. That means the probability to occur any phase is equal to the probability of occurrence of any other phase. So there are 6 outcomes possible, and that outcomes are 1, 2, 3, 4, 5, 6. So all these outcomes are equally likely. That means the probability of occurrence of any of this outcome is same. So the probability of a phase 3 to come up is 1 by 6. That also can be understood by considering this equation. The total number of cases is 6, and the probability and the number of cases in which 3 occurs will be 1. So 1 by 6 will be the probability for a phase 3 to come up. The probability of the dice coming up with an even number is 3 by 6, as there are only 3 even numbers on the die 2, 4, 6. So these are the possible outcomes. So we know that 2, 4, 6 are the even numbers. So the probability to get an even number when throwing a dice is 3 by 6. Probability to get a number that is less than 6 equal to 5 by 6, because in the all possible outcomes, these 5 outcomes are less than 6. So we can say the probability to get a number less than 6 is 5 by 6. Probability to get a number 7 is 0, because we know that in the possible outcomes, number 7 is not there. So probability to occur a number 7 will be 0. Probability to occur a number that is less than 7 will be 6 by 6, 1, because for all these outcomes, the numbers are less than 7. And another property of the probability is that the probability will always lie between 0 and 1. Principle of equal a priori probability. So we considered here the example of tossing a coin. So I already said that there are only 2 outcomes possible, either a head or tail. And the probability to occur a head is same for the occurrence of tail. In this example of throwing a dice, there are 6 outcomes and the probability for all these outcomes are same. We can consider another example here. An open box is divided into 2 equal sized compartments X and Y, and a small particle is thrown from a larger distance in such a way that it must fall in either of the 2 compartments. Then the probability of the particle to fall in the compartment X is equal to the probability that it may fall into the compartment Y. And all these events, in all these events, we say that the events are equally likely to occur, because all the events in these examples, the probability for the occurrence are same. So in the case of first example, both head and tail have same probability. So in the case of 6-faced cubical dice, there also all the 6 outcomes have equal probability. And in this example, if a box is divided into 2 equal sized compartments X and Y, and if you throw a ball, the probability for the ball to fall in X is same to the probability for the ball to Y, and such events are called equally likely occur. The principle of assuming equal probability for events which are equally likely to occur is known as principle of equal a priori probability. A priori means something we know earlier. So without doing the experiment, we can assign a probability for these events, because all the events are equally likely to occur. So in the case of throwing a coin or tossing a coin, we know that the probability for the head to occur is 1 by 2, because all the 2 outcomes have equal probability. And that is meant by the principle of equal a priori probability. Next, we study another term called frequency. So in the previous examples we considered, all examples, the events are equally likely. But we cannot say that in real life, all the events are equally likely. An example we can consider here, suppose a dice which is asymmetric. A dice can be made asymmetric by adding a little load to one of its faces. For example, suppose we put some wax on one face of the dice. If we put some wax on one face of the dice, that dice become asymmetric. In that situation, we cannot say that all the faces are equally likely to occur. So we cannot assign a probability 1 by 6 to the event of occurrence of any face. The principle of equal a priori probability will not hold good in such examples or such cases. In the above example, the two compartments are of unequal size. So in this example, we said that if two equal sized compartments X and Y, a ball is thrown, the probability for the ball to fall in X is same to the probability for the ball to fall Y. But if the compartments are of unequal size, one compartment is large compared to other compartment, then the probability is high for the ball to fall in the larger compartment. In that situation also, we can say that the events are not equally likely. If the events are not equally likely, we cannot apply this equation to find the probability. So in such situations, we can find the probability by finding frequency. So next we will study what is meant by frequency. Suppose we toss a coin n times and we find that head appears m times. Here we introduce a term frequency f of an event as f is equal to number of trial in which A occur divided by total number of trials. So we tossed the coin n times. So the total number of trials is n and the head appears m times. So m by n is called the frequency of appearance of head. There must be a relationship between frequency and probability. As the number of trials is increased, the frequency of the event progressively tend to stabilize and gradually approaches a constant value known as the probability of the event. And this statement can be understood by considering the example of tossing a coin n times. Suppose I toss the coin for 2 times. Then for the 2 times we may get 2 head or 2 tails or 1 head or 1 tail. Suppose I am tossing 10 times. I am tossing a coin 10 times, then the n becomes 10. So from our own experience, we know that around half of the times we get head or tail. So the number of heads will be near to 5. That means it may 4, 5 or 6. And suppose I am tossing the coin 100 times. Now n is 100. When I am tossing the coin 100 times, the number of times I get head will be very near to 50. So the frequency is 50 divided by 100. So very near, I will get a number that is very near to 0.5. If I toss 10,000 times, then we are somewhat sure that the number of times that we get hit is very near to 5,000. Similarly, if we increase the n very large, then the ratio m by n gradually approaches a constant. And that constant value will be the probability. So if we toss the coin for 1 lakh times, n become 1 lakh and m will be very near to 50,000. And if we calculate m by n, that value will be very near to or will be equal to 0.5. So we can define the probability P is equal to m by n in the limit n tends to infinity. So in this way, we can calculate the probability. And one speciality of this equation is that equation 3 is that here we can apply this equation even if the events are not equally likely. But to obtain sufficiently accurate result, trial must be conducted until the ratio m by n differs from one another by a very small value. So this statement is very easy. Suppose I repeated the experiment. That means I tossed the coin n times. That means n is very large. Suppose it is 1 lakh. So 1 lakh times I tossed the coin and I calculated the m by n ratio. And suppose I tossed the coin for 1 lakh and 1 times. Then again I calculated m by n. So we know that these two m by n values will be very near. So m by n differs from one another by a very small value. Then we can take that m by n is equal to the probability. Next, we are going to review some of the basic rules of probability theory. One is additive laws of probability. Let A and B are two events which are mutually exclusive. The probability of occurrence of either A and B. The probability of occurrence of either A or B. This is not and, either A or B is probability A or B is equal to probability of A plus probability of B. This is known as additive law of probability. Mutually exclusive events means two or more events are said to be mutually exclusive if the occurrence of any one of them prevents the occurrence of the others. Such events never occur simultaneously. For example, suppose we are tossing a coin. Then either head or tail, only one will occur. If head occurs, it prevents the occurrence of tail. And such events are called mutually exclusive. So if A and B are two mutually exclusive events and the probability of the occurrence of A or B is equal to probability of A plus probability of B. And this is known as additive law of probability, and this law can be understood more by considering this example. The card is drawn from a well shuffled pack of 52 cards. Calculate the probability for this card to be either a king or a queen. So the first event is the card becoming king. So the probability for the card to become king is equal to 4 by 52 because there are total 52 cards and in a pack of cards there are 4 kings. So we can say 4 by 52 will be the probability that is equal to 1 by 13. And the second event, the probability of drawing a queen, that is probability to get a queen is equal to 4 by 52. That is also 1 by 13. So the probability to get either a queen or a king is equal to 2 by 13. Next rule is joint multiplication probability. The probability of joint occurrence of two independent events is equal to the product of the probabilities of each of this independent event. An independent event means the occurrence of one event will not affect the occurrence of the other event. So A and B are called independent events if the occurrence of A will not affect the occurrence of the B. So the probability of occurrence of A and B together is equal to probability of A into probability of B. In the previous case, we consider the probability of occurrence of A or B. But here, the occurrence is together. That means the event A and B are occurring together. So the probability is given by P of A into P of B. Here also we can consider an example. A dice is thrown twice and obtained two numbers. What is the probability that these numbers are 6 and 4? So a dice is thrown twice. So the probability to get 6 is very clear, that is 1 by 6. And the probability to get 4 is equal to 1 by 6. So the probability to get 6 and 4 is equal to 1 by 6 into 1 by 6, that is equal to 1 by 36. Now we will study a concept of conditional probability. The probability for an event A to occur in the condition that event B has occurred is called the conditional probability and is denoted by P of A conditional B. So in this case, the events A and B are not independent. So the occurrence of one event will affect the occurrence of the other event. So P A conditional B, that means probability of occurrence of A conditional, the B is already occurred. So if A and B are not independent, then the probability of the occurrence of A and B together is given by P of A into P of B conditional A is already occurred. So this equation is very important. It says that the probability of occurrence of A and B together is equal to the probability of occurrence of A into the probability of occurrence of B conditional A is already occurred. If A and B are independent, then this term probability of B conditional A will be equal to probability of B. So this will change to the previous equation if A and B are independent. But here we consider A and B are not independent. So the probability of occurrence of A and B together is given by this equation. This also can be understood more clear by considering this example. A box contains 4 black and 3 white balls. What is the probability that two successive draws, the balls drawn are both black? So probability of first draw, a black ball, or the first drawn ball is a black, is equal to 4 by 7 because there are altogether 7 balls in the box, and among these 7 balls 4 are black, so 4 by 7 will be the probability. Now consider the second case. Probability of the ball in the second row is black. Conditional first draw is black is equal to 3 by 6 because one ball is already drawn. So there are remaining 6 balls, and in that 6 balls only 3 are black. So the probability to get a black ball in the second row conditional in the first draw a black ball is obtained is 3 by 6, that is equal to 1 by 2. So probability for the occurrence of A and B together. Here A and B is is the event getting a black ball in the first draw. B is the event getting a black ball in the second draw. So the probability for the both balls to become black is probability of A into probability of B conditional A. That is equal to 4 by 7 into 1 by 2, that is equal to 2 by 7. So here we considered the basic probability theory and the properties of probability. Now we will go to permutations and combinations. To understand the permutations, we shall consider again an example. Consider an example of 4 distinguished objects marked A, B, C, and D. Taking any 2 objects at a time, the possible arrangements are ABBA, ACCA, ADDA, BCCB, BD, DB, CD, DC. That means consider 4 balls, 4 distinguished objects marked A, B, C, and D. And suppose we are putting these objects in a box and taking two at a time. So when we take two from the box, the possible arrangements are these. There are total 12 arrangements possible. Note that here AB and BA are considered as two different arrangements. So all these arrangements are called permutations. So we can say if four objects can be arranged in 12 ways by taking two objects at a time, the number of permutations is 12. Symbolically, we can write 4p2 is equal to 12. This means that there are four objects and two objects are taken at a time. Then the total permutations is 12 and that permutations is shown here. Now consider instead of two objects, we are taking three objects at a time out of four objects A, B, C, and D. Then the possible arrangements are shown here. So altogether, there are 24 arrangements. So in this case, the total number, the permutations is 24. So symbolically, we can write 4p3 is equal to 24. That means there are four objects and three objects are taken at a time. Then the permutation is 24. In general, if the number of arrangements of n distinguished objects by taking r at a time is npr is equal to n factorial divided by n minus r factorial. So this is the general formula to calculate the permutations. For example, for P2, which we evaluated earlier, that means there are four objects and taking two at a time. So applying this formula, we will get 4 factorial by 2 factorial. That is equal to 12. Similarly, for P3, which here we obtained as 24. That is 4 factorial divided by 1 factorial. Applying this formula, we will get 24. So this is the formula to calculate the permutations. Now we go for combinations. Here we consider combinations, that is groups without considering the order of their placement, that is only meaningful combinations. The difference between permutations and combinations is that in permutations the order is important, but in combinations we do not consider the order. For example, AB and BA will be considered as one arrangement. Thus the combinations of four objects A, B, C, and D, taking two at a time are AB, AC, AD, BC, BD, CD. So here only 6 arrangements or 6 combinations because here we are not considering the order of the objects. Only 6 combinations. Symbolically we represent 4C2 is equal to 6. Suppose we are taking 3 at a time. Then the possible arrangements are ABC, ABD, ACD, and BCD. That is only 4 combinations. Symbolically, we can write 4C3 is equal to 4. That means we have four objects and taking 3 at a time. Then 4 combinations are possible. So the general formula to calculate the combinations is given by NCR is equal to n factorial divided by r factorial into n minus r factorial. So the 4C2 means we have 4 particles and taking 2 at a time. Then the number of combinations can be sorry 4C2, we have four particles and taking 2 at a time. Then the number of combinations can be calculated using this general formula 4 factorial divided by 2 factorial into 4 minus 2 factorial. That will be 6. It is clear that NCN will be equal to 1. NCN means we have n particles and taking n at a time. Then by logic itself, we know that the number of combinations will be 1. So when we apply this formula, also we get the number of combinations will be 1. Thank you.